Fire away.
Okay, are you seeing this here or are you seeing this here?
I'm actually seeing your desktop.
Okay, let me try extending it.
If you don't want to share the whole desktop, you should just be able to share like window by window. It has to work.
Let's do that. Professors
what's that again?
end up doing this where they show the wrong one. It's because it's easy to figure out how not to. Okay, so yeah, so let's do, I want to do a screen share, but I want to do this one. There we go. Okay, now you see one?
Actually, no, now I'm seeing just your, are you sure you're sharing that?
You're not seeing anything, okay.
Check on the Hangout side.
It says you're sharing your screen.
Yeah, no, it's funny, on the Hangout side and on the YouTube side, I'm not. Yes, please.
What are you actually seeing?
Well, on the YouTube, there, it's just catching up. So I'm seeing the top now. Now I'm seeing the full slide. Oh, that way on? Okay, cool.
Okay, so you can see the full screen there.
Yeah.
Yeah,
it's probably because you're on Wi-Fi, but we'll go with that. It's like so.
All right. My name is Rich Nielson. I'm a project manager of the solution stream, and I'm also a student with Georgia Tech right now, doing their online master's degree program. What I put together in this presentation is stuff I've been learning from my classes that I thought was kind of cool. So that's what we're going to be presenting. This is for Provo Data Science.
Yeah, Provo Data Science Workshop, or Big Data Utah.
Big Data Utah, Provo Data Science Workshops. So what we have here is the first picture here is actually AlphaGo beating the world champion in Go. That was actually a collection of algorithms. The center of the algorithm was a reinforced learning algorithm. So what we're going to be talking about is why isn't a reinforcement learning algorithm was able to beat Go, the world champion Go player, other tech algorithms couldn't. Prior to this happening, people weren't even sure a computer could ever beat a world champion in Go. It was a big deal not too long ago when IBM's computer beat the world champion in chess. But that was actually an algorithm really well decades and decades ago, how to beat a world champion in chess. It's a basic search. And it just took a while for the hardware to catch up to where it had enough memory to search out far enough that no human could beat it. So it really wasn't a giant improvement in any sort of techniques. It was just a matter of improvement in hardware. Go is a totally different thing. The number of the exponential explosion of what you have to search is overwhelming. And there's no computer that will probably ever be built that can just do a search to be able to beat people. And Go champions don't use anything like a search. They, the techniques in their brain, they don't necessarily fully understand the techniques in their brain, but use something else entirely. And so it's a matter of how do we capture that. And reinforcement learning allow them to do that. So let's talk about different types of machine learning quickly and kind of position reinforcement learning amongst them. So we have supervised learning, which is probably the one that you hear the most about. So if you think about machine learning, you're probably usually thinking about supervised learning. There's also unsupervised learning. And then there's other types, but we're going to compare that with reinforcement learning. Yes, that's Pavlov's dog. The analogy is not incorrect here. So let's talk about supervised learning. Let's say you have square feet and number of bedrooms, and you're trying to predict the sales price. So across the top here, the square feet of bedrooms, those represent the features in supervised learning. And the last column there, that's the correct values. That's, you give it the correct values, you give it the features, and it comes up with some sort of formula to determine how to use the features in the future to predict the outcome. Now in this case, since this is, I made these numbers up, so they're pretty close to the line. What you're really doing, the formula is the line here. Okay, so this would probably be like linear regression. And that line there is the formula that the machine learner comes up with. It just fits a line with the data in case of linear regression. Okay, and then there are other types of supervised learning, deep learning, it's neural networks. That's also usually supervised learning. Unsupervised learning is kind of more about exploring data. So, for instance, let's say you have all these dots here, and you say, okay, I want to see how that breaks down into 3 clusters. And then you might use clustering algorithm, tell it to do 3 clusters, and it will break them into 3 clusters. You can kind of see the eye, but that makes some sense. For some reason, those seem to belong together. Unsupervised learning is, like I said, really about exploring data. It's something that a data scientist does to figure out, okay, what's the structure of this data? It's going to go into the validation. Now, reinforcement learning is sort of in between supervised and unsupervised learning. I hate to say that. It is true that it's sort of in between, but there's something called semi-supervised learning that's far more obviously in between supervised and unsupervised learning. So reinforcement learning is kind of in between them, but really kind of its own thing.
Super quick question.
Yes.
You taking questions from the flyer? Or you want to
Sure. Go ahead.
So I guess the thing that when I hear anything learning, I'm like, is that deep learning? So maybe you could just dispel that or let us know. I don't know. Like, is reinforcement learning?
You can use deep learning with reinforcement learning. You know, it's deep reinforcement learning. But deep learning is specifically neural networks with lots of layers. That's what deep learning means.
So deep learning is like a subset of reinforcement learning? Is that a way?
No, it's a matter. Deep learning is that you're using neural network and then you're using multiple layers. You could typically you would do that with supervised learning, but it is possible to use it with reinforcement learning also.
Okay, thanks.
So they're like that you can mix them as you see fit. They're not really one or the other. Okay, so characteristics of reinforcement learning. Exploration, I'll explain that better later on. Delayed rewards, that seems kind of obvious that for reinforcement learning to work, according to that analogy of Pavlov's dog, it's got to be able to anticipate a reward and somehow come up with policy to get to that reward and get a reward somewhere in the future. Supervised learning, typically what you do is you come up with a formula, you come up with the model, and then you use the model. Reinforcement learning, it doesn't really learn from that point forward. I mean, there are ways to make it again, but typically you're just using the model. Reinforcement learning can be online, it can be continuous. All right, so it is somewhat similar to supervised learning in that there's some sort of good behavior that's similar to a loss function. Unsupervised in that there's no correct result that you're giving it. And it is just trying to explore there. So why was reinforcement learning able to beat the AlphaGo, the Go master, when other types of artificial intelligence have failed? Well, that's what the kind of answers we come along with. So with reinforcement learning, typically, there's probably different types. The type we usually study is going to be to solve something called a Markov decision process. Now, the Markov decision process contains states of some sort that you can move between, actions that you can take, and it has some sort of environment, and that environment, I should use the pointers, you can see it online here, so pointing. The environment has some sort of transition function, so you're in one state, you take an action that moves into another state. It has some sort of reward function. Under certain circumstances, you obtain rewards. So key assumption is, though, with the Markov decision process is that everything that you're tracking right now is everything you need to know. Right? You're not looking at your own history, you're just using the current state. this may sound very limiting, but this actually makes some sense. If you think about, say, physics, okay? The world runs on physics. Physics, you don't need to know what the history of a cannonball was. You need to know where it is right now, what its current velocity or acceleration is, and then from there you can predict its future. Okay? So physics is a Markov decision process, which means the whole world is a Markov decision process in some sense. That's probably stretching it like a little bit close to the truth. So also, you can always promote things. If you need something from your history, you can make that part of the current state. It's not as limited as it first sounds. Okay, so example of Markov decision process. This is a very simple maze. Okay, in fact, it's so simple, it's not even a maze. It's just 9 squares. There's no walls. It's the world's easiest maze. Start at the start, and you need to go to the end. You know, so you can get there any way you want. You go here, 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 there, and get your goal. And whatever you want to do, you can see states, and you can see actions. How many states and how many actions are there? Yeah.
Looks like 9 states, and in each square there's like 2 to 4 actions.
And it depends if you count diagonal or not. I'm not counting diagonal, so you're correct. So 9 states. Obviously, each square is a state. Actions, up, down, left, and right. I'm not going to do diagonal, because I'm trying to keep this as simple as possible mathematically. So here we go. Here's the 9 states, and these represent each of the actions. Okay? If you were to take an action that went off the end, it just moves you back to the same state that happened, basically. Okay? So you could count those as actions. I'm not going to count those. I'm going to assume that you're not going off the end here. Okay, so how might we solve this problem? Now, one thing that we can do is, let's say we knew the transition function. In this case, we do know the transition function. This table here represents the transition function. If you're in state 5 and you go right, you go to state 6. Okay, that's the table is the transition function in this case. Okay. What's the reward function? Well, if you're in state 3, you get 100 points. Okay, that's the reward function. Every other state gets 0 points. Now, in real life, if you were doing this with a computer, you'd probably want to say every other state is -1 point. There's reasons why that causes things to move along faster, converges faster. There's a number of reasons why you do that. But it also complicates the math when I'm trying to demonstrate math on slides to humans, so I'm going to stick with 0 for the presentation. Okay, so now there's something called dynamic programming. I don't know why it's called dynamic programming. That seems like a misname to me. I took 2 classes last semester. I took from Georgia Tech. I took AI for robots, and I took machine learning for training. In AI for robots, you use dynamic programming to have a virtual robot solve a maze, exactly like we're talking about. In machine learning for training, we used reinforcement learning to solve a maze, as a matter of fact. They were exactly the same problem that we were trying to solve in 2 different classes, but one was using dynamic programming and one was using reinforcement learning. And I have to tell you, my initial impression was, what is the heck, why would you ever use reinforcement learning? Dynamic programming is better in every way. It was faster, it gave a better answer. They both try to find some sort of optimal policy. I'll explain what that means in a second. Dynamic programming always found the optimal policy. Reinforcement learning kind of sort of found the optimal policy. So dynamic programming seemed at first to be superior to reinforcement learning, but some people would consider dynamic programming a type of reinforcement learning, others wouldn't. So I'm not counting it as reinforcement learning. It's okay to count it if you want. The thing that makes dynamic programming so good is that it has to know about the transition function. It takes the transition function, takes the reward function, and it solves for what's the optimal policy for each state. So right, you see here with these arrows, many of these arrows could have had multiple directions. So dynamic programming just picks one if there's 2 equally optimal in space 1. So this is one possible optimal policy. If you're in this state, go here. 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 You may go. If by some chance, let's say that there's some sort of stochastic process, it's random. Sometimes you say, I want to move here. We know robots in the real world don't always do exactly what the motor's telling them to do. Maybe it accidentally slips here instead for some reason. Then it says, oh, well, I'm actually in this state, and then it finishes solving the policy using the optimal policy anyway. So the optimal policy always tells you, no matter where you are, what you need to do. Now, this here is something called a value function. I'm going to be discussing that a lot more throughout. But you can see the goal here is 100. And what dynamic programming does to create this optimal policy is it says, okay, I'm going to discount. I'm going to say that if you are in a square next to the goal, then maybe my discount is 90%. These positions are worth 90 points instead of 100. This one's worth 81. These are worth 81 because they're 2 away. 72.9 is 90% less each time. 65 right here. And then for dynamic programming, this presentation is not about dynamic programming, but what you would do is you would say, oh, well, I'm here. Which square can I go to has the best possible policy? In this case, both your options are the same. So let's say you go here. It says, okay, what's the best now? Let's going to discount that one because that's lower value. So it's going to go there. Then it's going to say, okay, which one now? It's going to say, oh, well, I got a choice between these two. So it goes here and then here and we solve. And that's how it comes up with the optimal policy. Now, here's the thing, though. What if you don't know the transition function? How often do you know the transition function in real life? Okay. We talked about machine learning for trading. I used reinforcement learning to come up with an optimal policy for the stock market. Okay. Can anyone tell me the transition function of the stock market? Okay. If somebody knew it, you'd be very rich. Okay.
Just buy some Ethereum and get rich. Isn't that how it works?
Yeah. Well, you know, that's how some people think.
That's what everybody's saying out there.
Okay. So in fact, we don't even know the reward function for that now. Okay. So most things in real life, we don't have an optimal policy. We don't know the transition function. We don't know the reward function. So you can't use dynamic programming to solve those, even though they're a Markov decision process, because you just don't know it. All right? This is where reinforcement learning comes in. So now we're going to stop and we're going to do a little bit of philosophy that will seem out of place, but it will make some sense later. So what led to this is we're wondering, you know, if only we come up with an optimal policy without knowing the transition function or the reward function. Now, this guy here is named Alan Turing. Well, actually, that guy there too. Everyone has heard the name Alan Turing before and seen the movie. So, what is Alan Turing famous for? Enigma Machine. If you've seen the movie Enigma Machine, what else is Turing test? He's probably most famous for the Turing test.
It's actually the most basic, primitive model of a computer, right? The computational model.
The Turing machine.
Thank you. That's it.
There's something called, this is what he's really most famous for amongst his colleagues.
This is what you see if you.
This is the non-pop culture version of Turing.
If you have to do an assembly in your, into a computer organization class, that's what you use, right?
If you get a degree in computer science, say a bachelor's degree in computer science, they will force you to take a class called computational theory. Does anybody here take computational theory? All right, awesome. Honestly, what did you think of the class when you first started into it? What kind of came to your mind as you were taking computational theory? Be completely honest.
It's the very basic.
How the hell do I program this? Okay, yeah. What?
It's the very basic thing. The
Most basic. Okay. To me, it seemed totally irrelevant to anything. It has nothing to do with computers, as far as I can tell, other than this very basic idea. What's the point of actually teaching all this? It was a bunch of mathematics, it didn't help the program. It seemed, and that was how, at least I remember most of the people in the class feeling about the class. Turns out it's a really, really interesting subject. Uber interesting subject. Completely dryly and, without any sort of practical application, and so it's hard to figure out what it's all about. Turing machine is a really basic machine. It's got a read-write head, and it goes along a tape, runs loops along a tape, and Turing and another guy named Church were able to prove that every single type of computer that you could build, a Turing machine could simulate. Okay? It's a universal machine, computer machine. Okay? If you have a super modern, computer today, a supercomputer, it's still actually just a Turing machine in terms of what it can compute. Okay? Whatever limitations the Turing machine has, so does your supercomputer. And that's what made it actually kind of cool. So now, this guy here, anybody recognize him? Probably not. He's probably the second most famous physicist after Stephen Hawking today. His name is Roger Penrose. He's Stephen Hawking's teacher. And he gets quoted a lot. We probably read quotes from him or had people reference him, but you just didn't know who it was. It's one of those things where once you know who he is, it's like, oh wow, I can't believe how often I see his name crop up. But until you know who he is, it's just some scientist as far as you know. Now, he's a smart guy, and he pointed out there's actually a bit of a difference between how Church formulated the Church-Turing thesis, which was the idea that Turing machines are a universal computer. They can't prove it. There's no mathematical proof for it. But they've never found a counterexample. Okay? Not quite true. Quantum computer is sort of a counterexample. And they actually now have something called the Church-Turing-Deutsch thesis, which encompasses quantum computing. Okay? But for our purposes, the Church-Turing thesis has never really found there's no exceptions to it that we know of. We don't have any proofs that it's truly a universal computer. So it's a theory, it's a scientific theory, that it is a universal computer. Penrose pointed out that Church and Turing formulated the thesis a little bit differently and most people missed it. So one of Church was a little more, he wasn't as bold. He said, it's the Turing machine or the Church machine is equivalent to, you can run any type of algorithm, is what he said. But he kind of left open the possibility that maybe there was such a thing as a non-algorithm. Not that it's easy to contemplate what that would be, what that concept even means. Okay. Recognize that in science, we do things in terms of math. We do things in terms of algorithms. So he was bolder, and he made the claim that all of reality can be simulated on a universal computer. Okay. And we don't know of any exceptions to that, any more than we know of exceptions to the Turing machine. Now, David Deutsch here, physicist, probably don't know him. He's a world famous physicist, if he were a physicist. Okay. He is the physicist that created quantum computational theory. Okay. So Turing created computational theory. David Deutsch here created quantum computational theory. He took Turing's version of the thesis, which Roger Penrose calls the Turing principle. Reality can be simulated, always be simulated on a universal computer. And he kind of ran with it and said, what are the philosophical, what can we learn philosophically from that principle if we just accept it as a true theory? And which is what we do with scientific theory. We accept them as true, even though they may later be falsified. And we run with it. Okay, so now back to the presentation. I'll come back on this a little bit later. So what we have here is an explanation of something called the Q-learner. And I know this is like really easy. I mean, this is like uber simple stuff up here. So I'm sorry, I don't mean to insult anybody's intelligence, but kind of leave it up there for a second so you can see the proof and kind of understand it. And I kind of get the feeling maybe this isn't so simple. That's all right, I'll explain it. One of the things I have to say is I don't know why mathematicians use such complicated little symbols that nobody else understands. They just put it in code, everyone can understand. everyone, at least all programmers understand.
Because they can't do it. Oops, sorry. I said
Yeah.
we can't do math, so.
All right, so let's talk about some things, and this will help us understand this proof and why it is a beautiful proof. And this is the theoretical basis for the reinforcement. So here we have our, I already talked about this, but our very simple maze, and it has a reward function. Reward function is, you're at the goal and you get 100 points, right? So that's what reward function is. Value function we already talked about too. I mentioned that dynamic programming can solve for it. So it just discounts. So notice the difference here. You only get 100 points at this place. You don't get 90 points for being here. Being here is greater than the value of being here because you're closer to getting 100 points. If you're familiar with economics, you understand the idea of net present value, discounting in the future. Okay, it's something, 100 bucks in your hands now is worth more than 100 bucks a year from now or 2 years from now. Okay? That's all they're doing here. Okay, they're coming up with some sort of discount to account for the fact that it is better to be here because it's only one move to move here than it is to be here, which is 1, 2, 3, 4 moves to get here. But you actually get no reward for being here. So value and reward is a different concept. Right? Those are the functions. Transition function was that list between transitions or any function that creates a transition. That's what a transition function is. Q function is the next thing I'm going to have to explain. So the Q function is kind of arbitrarily made out. It turns out it's useful. Q function is very similar to the value function. It gives a slightly different set of values, but it works out the same. What we've got here, though, is we're assigning a value to the actual actions from the state. So value function is based on states. Whatever state you're in, what's its value? Q function says, if I'm in state 2 and I decide to move right, that the value of that move is 100 points. It's going to get 100 points. Okay. So that's what the Q function is.
It's easier to represent this as an
To represent it as what?
edge-weighted graph.
Well, it is underneath, right?
It is essentially, right? If you want to show it.
Yeah, so it's typically actually represented as a on the right. It's a, so I'll show you in a second what he's actually represented as. Now, an optimal value function that's created from the Q function, it looks very similar to the value function that dynamic programming creates. In this case, we count them both separate. And what we do is we take the max move. If I'm in state 2, what's the max Q value? In this case, it's 100, so I assign 100 as the value of that state, et cetera, et cetera. Okay. The final, and then the last thing is the optimal policy. I'll be familiar with this. It's whatever state you're in, what's the best move for that state. Okay, so now let's go back to the mathematical proof. So what we have here in plain English, the value of a policy for a given state is the reward of that state, plus the discounted reward of every state that comes after according to that policy. Okay. Value of the policy for a state at a certain time is equivalent to the reward at that time, plus that's just the discounted gamma. The discount rewards of the future. Each time you move one movement into the future, you continue to put an exponent on the gamma so that it gets more plus and less, 90%, 80%, 80%, etc. Okay. And that's really just the same as what we're talking about here, the value function. So that's pretty straightforward.
Real quick question. I'm not always the best at recognizing this Greek letter. So that's a lowercase gamma, and that's not the same as a gamma function, right? Like,
yeah, it's just a discount value. So it's like 0.9 is what I'm using.
But it's not like doing a factorial on each term. Okay, cool.
Okay, so this just says that the funny Greek, letters just mean that the optimal policy is the one that has the largest value function for every state. This means policy, that means optimal, it's equivalent to argmax, which just means the best policy for a given state here. And this just means for all states. Okay. Again, that's pretty straightforward. Of course, the optimal policy is the one that has the largest value for every given state. Okay, if you had a policy that had a lesser value, then it wouldn't be as good. It would be an optimal policy. Okay, you see that here, how this translates between the optimal value function, translates to the optimal policy. Just a matter of, we're moving towards the one that's going to be the highest value. All right, so this one here, it means the optimal policy for state S is the best action that gives you the highest reward plus the highest discounted reward. So basically we have policy, the optimal version of policy for a given state is equivalent to the argmax. The difference between max and argmax, max is the value itself, argmax is the action that gives the highest value. Argmax A means action that gives the highest value. So whatever action gives the highest value for this combined formula, which is the reward for the current state you're in, given that action, and the discounted of the transition, that's the transition function, to the next state, in other words, the next state. The value, the optimal value of the next state that you end up in, if you took that action in that state. Okay. Again, it's actually fairly straightforward what they're saying.
Wouldn't this be prone to being stuck in the local maximum? Stuck in the
What's that?
Wouldn't this be prone to being stuck in the local maximum? Like if you're actually in a survival, then it seems like it would be prone to being stuck into a region that had a max versus one solution.
No, that's a good question. So in a Markov decision process, first of all, yes, that's exactly what happened. Decision process, it's theoretical. So they would say, well, if you ran it forever, it would always, I'll show you why, it would always eventually find the optimal policies. Guaranteed to always find the, other than this, guaranteed to always find the optimal policy and never get stuck in a local maximum, provided you run it forever.
You start in an initial random state in that scenario?
That is one of the strategies.
Okay.
You wouldn't always, there's different strategies depending on the actual problem.
Sorry
that
for
you solve.
the
No, good questions, excellent questions.
Can I ask
I
a question?
that.
Yeah.
So when I've seen stuff like this before, I don't know exactly what the difference is, but I usually am seeing that like the V-star, for example, will be computed based on the V-star for the states surrounding it. And so I've seen formulas, for example, that have V-star on the left and then have a V-star of delta S plus 1 and A. So basically, that's why you have to use a dynamic program, because you have to solve the states that are closest to the end first, and then solve what.
That's what this is actually saying. Let me go back one. It's saying V star of the transition function, but that just means the next state. The transition function is if you're in this state and you take this action, it moves you to the next state. The thing is V star of the state next to it. Okay, that's exactly what it's saying.
So V star is the value of being in a given state.
Yes.
And pi is the policy.
So V star is the optimal value of being in that state, which that probably collapses to be the same as the value in most cases.
Yeah, it's the value if you take the optimal policy.
Yes. So yes,
So that depends on solving the optimal policy.
So this is in fact saying you're getting your value from the next state. Okay, but you're adding in the reward for this state.
But in order to actually solve this, you have to do what we were talking about a second ago, which is backpropagate, which is, in other words, you have to solve the ones that are nearest to the end because those are the ones only you know the optimal
That's
for
correct.
those.
That's how dynamic programming works. It solves the one closest, and then it solves the next one, then it solves the next one, and you keep doing it.
Yeah.
Okay, so now we're defining the Q value, which, like I said, is a little bit arbitrary. It's a lot like the value, except it takes actions into consideration. Okay, so the Q value of this state in action is equivalent to the reward of being in that state in action plus the discounted optimal value of the transition of the next state. Okay, so it's the Q value of a given state S when taking action A is the reward for state S given action A plus the discounted optimal value of the next state. Okay, that's just by definition. All right. So now note that this seems a lot like it's a restatement from the last slide. The last one we said the optimal value policy for a state. In fact, it really is identical to the last slide, except that we have this argmax for the action, and here we're saying for whichever action. Okay. So all you would have to do to make an equivalent is say, well, the optimal policy for a state is the argmax action A for the Q value. Right, does that make sense? It's actually very straightforward also. Okay. Or in other words, the optimal policy is the one that maximizes the Q function. Okay. All right, so now, if the optimal policy for state S is the action that maximizes the Q value, then what is the optimal value for taking the optimal policy in a specific state? Well, that would be V star S equals the maximum value of the Q function. Here, that just means the next state. Right? It's not the next action, it's the action you're about to take. Okay, or in other words, the optimal value of the state is the action that you'll next take that will give the highest value. Now, super obvious example here. Let's say you're in state 5, and you have actions up and right. So the value of being in the state, what's the optimal action? You've got 2 of them, 90 to go here, to go up, it takes you here, and 90 to go right, which takes you here. Okay, they're actually equivalent in this limiting ways. I'm just saying the value of being in the state next to the goal after discount. So the reason why you justify putting a 90 here is because that's the best actions. The value of the optimal value of the state is equivalent to whatever is the best action for that state. So put 90 here as the value because those are the 2 best values you can get out of the Q function. That makes sense? Okay. Again, none of this is really that hard. They make it look a lot harder than it actually is. Okay, now, here's the beautiful part of the proof. That in the textbook, they talk about, and I didn't get it at first, but as I started working on the actual assignment, it finally dawned on me what it was they were trying to say. Okay, so we have that the optimal value of a state is just the max of the next action of the Q function. Okay? That's actually a self-evident truth from the last slide. Therefore, the Q function for state in action is equal to the reward of the state in action plus the discounted max of the next action of the Q value of the transition to the next state, with that next action about to take. Does that seem obvious also now? Why that would have to be true? Because the only difference here, we just substituting the 2 previous definitions. So you had the definition of Q, and you had the definition of the optimal value. You're just substituting them in. That's all you're doing here. Here's the cool thing though. Q is now defined in terms of itself. So Q is equal to the reward plus the max of the Q of the next state in action. Okay? So therefore, given that function, this allows us to come up with an algorithm that can estimate the Q function without knowing the transition function or the reward function. Here is how you do it. Start with the Q values in a table for every state action pair. Come up with an initial, you need to have kind of an initial Q function approximation. In this case, maybe set all the zeros. Your initial approximation can be random, just zeros, different strategies with that. But you know it's basically completely wrong. That's okay. It's still an estimation of what Q ultimately means. Then you follow this algorithm. So the Q algorithm is you select an action and you execute it, and then you receive rewards. Now, we'll talk about how that works, but in real life, rewards happen. Stock market, your stock goes up, that's a reward. It goes down, it's a negative reward. Okay? You don't have to know the reward function to know if you just got rewarded positively or negatively, because real life does that to you. So what's the reward for having moved to that state? Okay, so now you observe the new state, and in that new state S prime, you go into the new S, and then you update your table entries as follows. The hat over the Q just means it's your approximated version, which started off as all zeros maybe. new value of SA in the table gets the reward plus the discounted max action for the next action of the state that you just ended up in for having taken the move. Okay? In other words, in real life, if you a robot, you turn your engines on, you actually do move through your state. Okay? In the sense where that state is, that's the problem in itself. And if you're in the market, you move to some sort of new state. I'll show you what that state represents in the market. And then you receive rewards. And as long as you just keep iterating, that Q value, your approximation of the Q function, is guaranteed to always get closer to the optimal policy. The optimal values. If you ran it forever. Luckily, you don't have to run it forever to get close enough to make it useful. All right, so let me try to go through this one more time just to make sure we got this. A value, this is defining these three here, defining what the value of state is, defining an optimal policy for state, and defining what a Q function is. So the optimal policy for a state is defined now in terms of the Q function, just a matter of replacing things to come up with this. Notice that these two here are identical. So part of the definition of the optimal policy and part of the definition of the Q function are identical there. Notice that these two are identical, okay? And that these two are identical, all right? Because of that, we can define the value of a state as being a matter of the max next action of the Q function. Now here, we're saying that this is equivalent to that, but just move one state forward. So that's why I put a green box around it. Therefore, this must be true. Notice, there's Q again. There is a form of our red box again. There is a form of our Q value. Just moved over by a state. And max A. Therefore, this has to be true, which means the Q function can be defined as an approximation without knowing the transition of the reward function. There's our Q. There's a red box. And, oops. Okay, and then the last thing, of course, is that the optimal policy is what we're really after. So to summarize, the Q function can be estimated from the real world reward plus our current estimated Q function. The Q function can create the optimal value function or form of it. The optimal value function can create the optimal policy. So the Q function and real world rewards, we don't need the reward and transition function. We can come up with the Q function all on its own. Interestingly, and I don't have a slide for this, it's actually possible to then approximate the transition function. Okay, so now, what does this all mean? All right, so Q learning can learn any unknown function, provided that it can be framed as a Markov decision process, because it's going to be framed as a Markov decision process. It has some sort of natural way to value rewards, and it's tractable. There's such a thing as problems that it can solve but not in a tractable way, so there's can't do it. That's true of the Turing machine model. That's part of what, that is one of the main things you study in computational theory is what type of problem is tractable, what type of problem is not tractable. Okay, so remember the Church-Turing thesis says that everything is a hidden function. There's nothing that is not a hidden function if that theory is true. That's our best theory. Which led to this quote that I found in the book Deep Learning with Keras. Reinforcement learning seems to be a general learning algorithm that can be applied in a variety of environments. It may even be the first steps to a general artificial intelligence. I see why this statement would be true, why this is not just someone making a wild statement. It's mathematically provable that there's some sort of generality to it in the way it functions. So machine learning is, in fact, about modeling reality's hidden functions. All of machine learning is. So anytime you do supervised learning or do deep neural networks, you're trying to come up with some sort of model that approximates the function of the world. Okay. Reinforcement learning is cool. It's type of machine learning. It approximates the function of the world just like everything else, but it does it using the rewards that exist in the real world. So basically, just feedback from the real world allows it to come up with its function. All right. So what are the limits of machine learning? I think one of the things that this when you start thinking about is that the limits of machine learning may be equivalent to human brain. And anything that a human can do, machine learning can, in theory, do, but the right algorithms to do it, that the right way to frame the problem to do it, and we don't in most cases. But in theory, it can be done. Right? Okay, now, with all that theory behind us, let's talk about the actual practice of how this works.
Quick question before you kind of roll over.
Yes.
So we forgot to give people an expectation, also a few people watching online. Like, how long are you going to go? Are you going until 4 o'clock or 2 o'clock or 2:45 or what?
I'll probably be done by 2 o'clock.
Okay, cool. And then we'll do a little Q&A after that.
Okay,
cool, thanks. Yeah, I don't think I'll hold you to it, but I'm just trying to get
yeah, no, that's
some
fine.
people a rough idea. Thanks.
Okay, so let's talk about this. So what we have here is the transition function. Oh, sorry, this is the Q function. Okay, so we've got states, we've got actions, and our initial values for the Q function is 0, 30. Okay, we've got the current state, which is the start, state 7. We've got our very simple maze, the concept of a reward function, a goal. And we have this concept here of how you can move between the maze, but we don't know this. This is how dynamic programming is solved, is by knowing that. We don't actually know that, but we just know it exists. Okay, so the Q learning algorithm we have, we've got how you update the Q function. This here, I'm not allowed to show you my actual code, unfortunately, because that would be a violation of code. They can look up the answer to the class that I learned this all from. But this is a little snippet of code here. There's one thing I haven't talked about that has to be added in. In real life, the way you would do the Q function is you would have an alpha. I haven't mentioned alpha up to this point. You just gamma, the discounted learning rate. Alpha really just simply says, look, we're gonna actually update the Q function based on what it currently is. The rest of the algorithm mixed with the reward we got in the next state, so that it actually slowly converges, and it doesn't just change every single time with some wild number. We want it to be kind of a slow convergence. What's that?
Alpha is like a learning rate. That is.
Yes, alpha is like a learning rate. So it's really the same concept as the learning rate. Okay, so now we have our reward function at 100, and we've got our droid in the maze. So now let's say this droid is just initially, when we start running the Q algorithm, it just randomly, it's all zeros. And under the circumstances, I said we're going to give a reward of 0 to each state. So basically, every single move is exactly equivalent as far as the sort of its current Q function, which is also zeros. So it basically just wanders around the maze, just randomly. Okay? And then maybe just by chance, and during that time period, because I'm not giving the native one reward, you can see the formula here that the Q function keeps getting updated to 0. So it just moves around and it just already at 0, so it just updates it to 0. Okay. Now, just by chance, it happens to find the goal, right? And it scores 100 points. And it gets feedback from the maze that it got 100 points. So it says, okay, I now have something to update my function with that isn't 0. So it says, okay, 80% of the old one, that's still 0. 20%, this is the learning rate here, of the reward, plus 90% of what it used to be for the new action state. Well, that's going to be 0 times 80, 20 times 100. So the value comes out to be, I did the math right, value comes out to be 20. So it updates the Q table to have a 20 here. State 2 to the right, now it's the Q value of 20. Okay? Because that's what it did when they got the reward. Okay? And that's obviously just a portion of the reward. Now let's say, we say, okay, we found the goal, set it back to the beginning, it starts wandering around the maze randomly again, and it just so happens that it ends up in state 1, and by chance happens to move right. Well, the moment it moves right, it now is in state 2, where the Q value has something that's non-zero, okay? So it says, oh, look, my max of Q is non-zero, so I'm going to update state 1 based on that. So 80 times this, 20 times this, throw these numbers in here, 18. So suddenly, 1 to the right gets an 18 for this Q value for program. Okay. And it works a little like another program, okay, where this is now, if you were to take the value function of these and just take the max Q, this one would now be worth 18, this would now be worth 20. It's actually out, so, okay.
Yeah, I think there's a arithmetic area.
Oh, is there?
Yeah.
It should be like 4 or something. Should be 20, about 21.
Oh, you're probably right. Yeah,
You get the idea.
okay, now, here's the best thing about it. It knows that right in state 2 has the best value, which is to go right again. So now it goes down, knows, go right, and finds the goal. Okay. When it does that, it runs through the numbers again, and it updates it to 36. Okay. It will start to converge to an optimal Q.
Is there a linear algebra solution for this conversion on this one? Matrix and self-multiplication. Feels like it's got that.
Well, for a maze, yes. So yeah, you could come up with, I'm sure dynamic programming could be turned into matrices and solve these questions. All right, so this is hypothetical, but over time, it converges to what it would be if you were solving it with dynamic programming. Okay, so it starts to say, oh, if I go to the right from state 1, I've got this backwards. Should actually be 90 at the top and 100 at the bottom. But it starts to converge to the numbers, and it starts to say, oh, well, if I'm in this state, I've got the best value, I'll go that way, and that is the alpha pulse. Now, getting into local max. So let's say that our initial path that the robot takes is here, 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 here. Well, what's going to happen is it's going to perpetuate out backwards. And let's say, just by chance, it keeps taking that path. Okay? It will end up with Q values that send it here as the optimal policy. And that's the local maximum. So how do you deal with that? Well, the solution is what we call the explore-exploit trade-off. Okay, so basically what that means is that some percentage of the time, probably a decaying amount, we're going to have the robot take a random action. So instead of following what it thinks is the best policy, you just go a different direction instead. There's other ways you can do that. You could also, in a case like this, put it into a state and take an action. Put it in a random state and take an action and use that in this particular type of problem. But that explore-exploit trade-off allows it to slowly get to the optimal policy and define what action is. Now, obviously, if you were to do that in a number of times, you would always find the optimal policy. The only thing that's actually guaranteed. Since in real life, you have to do a finite number of steps, you actually will end up with something that's a local maximum that's close. For this easy, you would probably find it exactly, right? But when I actually did, I'll show you with my actual Q-learning robot that I did for the class, it doesn't really find the optimal policy, it's just close. All right, so let me show you some real code here. I may put this up so we could, in case I couldn't run things or if something went wrong, but this is a new computer. So I've got the code here from a Q-learner from my machine learning for trading. And Oh, it's not, okay. I have a hard time seeing it now.
We can switch the screen. or something.
Okay, so I run the Q learner. First of all, notice that it's quite fast. Okay, the maze that we're trying to solve here. Okay. There we go. The maze that we're trying to solve looks like this. Okay, and it's got walls here. It's got 2 pits that. If you fall into it, it's a negative reward. So much more complicated.
Is there a quick step to get us a much bigger spot there?
I don't know. Let's see. You know what? Let me just show you here. This is the Q function. Let me go back to my slides. I've got a copy of this on my slides. Okay. So we have here the actual maze. This is the optimal policy that it found. You can see that it's not really an optimal policy. Like, what's up with all here rather than sending you away from the big track, right? But there's only a few that are wrong. Okay, it came close.
Which corner are you starting?
It's starting like right here.
Okay.
It's the 2.
Okay.
Okay. And this is the path that actually came up with. It's somewhat random with the robot moves. It may get off track. So boom, here it follows this. It gets pretty close. It wants to stay away from the pit traps because that's sort of negative 1,000 or something. And it finds it can find it in any maze you come up with. It did a pretty good job and it's fast. Okay. Now, the whole thing that I just went through with the theory was to explain why reinforcement learning is better than dynamic programming, and that's because you don't need to know the transition function. So this is one project, but now here is trying to deal with. So I picked a series of indicators, like say ball patterns. The ones I came up with were pretty simple. Obviously, it would be better if we had better indicators. And what we have here is the benchmark. So here you just buy a stock and hold it basically. And that's what it does, it's the benchmark. This here was me doing my best to find indicators that would beat the stock market. I got to tell you, I spent, that was probably the longest project for me in class because I just couldn't find it. It was really hard to solve manually. And I would try one thing and I'd end up lowering the benchmark, and I'd try something else, and it would maybe peak just above it for a second, and then you run it again and go lower. And try to find something that was anywhere near consistent, just very difficult. This is what the best I could come up with. This here is the Q learner on its first try. Boom, solved. Now, of course, this is the training. This is, of course, it's going to be more.
What is that? What's the left scale? Is that absolute numbers, or is it relative somehow? Or
It's the value of the portfolio.
okay, so we're not looking at like relative performance. This is just absolute value.
Yeah.
Okay, that's cool. So you had to actually go from 2008 October to like May. What was the bottom in 2009, like May 3rd or something?
Yes.
So what was it purchasing to have?
It was like JP Morgan.
Yeah, probably finance amounts to it.
Yeah.
Oh, okay.
All those bailout companies were like $1-2 and then spiked, right?
Yeah, I thought Citigroup broke the block like in May, not back in October. Well, anyways, regardless, go ahead.
So the Q learner solved it very quickly and did a much. What took me hours to find this much improvement, it did that much more instantly, which was very cool. In real life, the problem, of course, is that the function of the stock market is constantly changing. So what your Q learner has learned is not going to do as well. This is typical machine learning. The test data doesn't perform as well as the training data. So, by the way, this is the bias in the longs and shorts. That it came up with, which is kind of cool. Okay. It didn't charge me with the sake of the experiment. We used commission. That would probably screw everything up.
Or taxation.
So
It didn't do that on the portfolio, the Q learner.
yeah,
So there's no.
that's right. There was no transaction fee, but there was slippage. So like, you wouldn't actually buy it quite what you wanted to buy. So.
So in a way, let me see if I can rationalize what you're saying there. There's some sort of, you're not going to find a perfect stock market solution, but it found a good solution to try to maximize portfolio value as if that were the solution in this one.
That's right.
Navigate between different positions.
That's right.
They were states.
So now what's the state? What is the state for the stock market? It's literally, so here's a Bollinger Band. Bollinger Band, how we're used to seeing it where it shows an average of up, and down, and low band. This is a single indicator that takes that penalizes the whole, so you can use a single value. But basically, where are you compared to the band? This is where you're, above top band. This is where you're below the bottom band, etc. Okay, so now as a continuous value, or at least the Q order as a table that would never work. So what you do is you decimate. So you make it so that it's just 0 to 10. Whatever. And that is the state. Okay, the state is what's currently, I had like 3 different, I think I used up to 6 different values or something after a while. I had 3 values in there that started to overflow. The computers ran on it, had to do the table together. But I had a Q table that had millions and millions and millions of cells based on these hypercoded tables. Okay, this was my final out of strategy, for out of sample. So this is now the test set. Not nearly as good, but you can notice that it still beat me. And it beat me fairly regularly when I would run it over and over with different random seeds or whatever. It beat me more often than not. Mine was so bad that it didn't make a single trade until this point. And that was the best I could come up with because it was very, very difficult to come up with good indicators since that's not my area of knowledge. Here's the trades, longs, shorts, on that. This would be for the keyword. And that's it. That's how it actually works. So that was the thing that I found so interesting about this was the fact that ultimately the Q order was general purpose. You could just literally build it, what it makes, and then without modifying it, have it solve the stock market. Okay? What changed was the wrapper around it. And I was actually really amazed at that. I was surprised it worked so well. And made the final project expecting as the Q order. By the way, in the actual class, you have multiple options. I chose to do a Q order. Different types of machine learning. Any questions?
So one question about when you ran Q-winner on the 2009 data, you're running it over and over on the same data, right? And then to train it.
That's right.
So it seems like if that was the case, if you find something that's near optimum, but like someone else was saying with the maze, it's like you ran on the same maze over and over and eventually found the best way to short and long over the whole.
It didn't get anywhere close to
Really?
you have certain constraints for the whole thing has to run under these habits.
Oh, okay. The optimum would be almost infinite. Like if you made the perfect trade every day, you would max out.
I didn't show it, but I do have a graph of the optimal, and it's much higher. Twice as high.
Because you could buy and sell over just like a tiny increment where something jumped really high and all you have to look. But if you work as hard as good for 2 seconds to find something that would do really well, and that's what.
So, but I suppose that that's also, you probably never could get to exactly
That's the part of my question. It wasn't quite fair completely because it had access to the historical data they got to look at. Whereas if you were to use it to actually try to make money, you have to do it. You should know there's.
That's typical of machine learning, though. The real thing you're going to do with it is something that's never seen before. You never perform that.
Generate their own. Action. They'll just guess. You're right. relays it.
It was, just, what's it? Any other questions? Yeah, I don't know that. You know, I think, I don't think it would work very well with these. You'd have to really do more research into what we're doing.
I don't follow you. 90% of the other reports of last year's outputs. Oh, yeah. It's silly. If you didn't, you guys last year.
Well, let me, unless anybody else had a question, I was going to just like ask more of a blanket question. Like I think it was last month, you were sitting here and you made a statement, I'm going to overgeneralize it. You said, like, basically, okay, I'm going to really overgeneralize. You said basically all machine learning is linear regression, even if it's dressed up as something fancy. So I know I'm misquoting you. Oh, neural network, okay. Because I guess, like, kind of tailing on your comment, I mean, you know, like, what's the saying is that, you know, the generals are always fighting the last war. You know, like, who knows what the black swan or whatever's going to happen next is something that, like, no one can see right now, right? Like, what's that? Yeah, and it's really true. And so the same with financial, right? Like, everyone's looking in the past as to see what the next big crash is going to be. And, you know, just if you look at, like, sentiment, I mean, it's pretty crazy right now how positive everybody is. So my question is this, like, how much does past data matter in doing regression or any kind of machine learning technique when, like, the future data could take a different path? Like, how does machine learning actually, does machine learning really predict?
That is actually a completely fair question.
Okay.
And that's a good question. So obviously there's a lot of companies using machine learning because but I think we don't really know. It's entirely possible that the market is something called the efficient market hypothesis. If the market, only support of the efficient market hypothesis is true, then machine learning can't allow you to earn money because it's really just around there. So it'll find something that doesn't really do.
Okay.
So it kind of depends on which hypothesis, which version of the efficient market hypothesis. So let's say that if information in the market is completely efficient and everybody knows exactly the same things, then no one really has an advantage in temporary data.
We had a really good example in 2007. The Goldman Sachs assholes were false swaps. So that means a minimal risk on the downside. Right? They assumed that these things could never go into a seriously negative value. And that was part of the model that was messed up. These were, you know, derivatives on debt on derivatives on debt, right? And so we're all lost because their model was. And even if we have a historical trend for 100 years that shows a nice time series analysis with a lot of cyclical and seasonal trends in the market, there was always the go to zero possibility that has to be factored in if you have mathematical.
So, has anyone seen The Big Short movie? Okay, so to summarize what happened with the Great Recession and this mortgages.
Okay, now you're going to start a whole, there's like 17 different viewpoints on that, so go ahead.
Okay, so the reason why nobody thought it was possible to have that many mortgages go back simultaneously because it had never in the history of the world happened before. Okay, so they were giving it these really high ratings, and there's also some collusion going on. But I think it was justified in the markets, right? Yeah. Yes, a house and a mortgage is a AAA rating because that is literally the only history we have. And even during the Great Depression, the discount farms, almost nobody lost their homes. They would do whatever's necessary to keep their homes.
Of course, people also put 50% down payments on their houses back then. So.
Exactly. What they did not take into consideration in the models was the fact that they had never in the history of the world been set on mortgages.
Right.
And they did not know how that affected, they had no clue how that actually affected their model. And the answer is it moves the model from out.
Yeah.
Okay, now you can have giant numbers of defaults on mortgages because half the people are upside down. So why not default on the mortgage? They have nothing to do with this.
Yeah.
Okay, yeah.
When I was in graduate school, as a master's student, I was described a mathematical model for options. And this was back in 2005, so it's before it happened, 2007, I think. But it's an interesting model, but he also explained that certain assumptions should suddenly that model is making lots of people lots of money and all this information. And it required a large scale of capital.
That was 98, yeah. That was actually the smartest guy from Harvard.
So it's not just something that happens with any kind of.
Yes. Has anybody read the book Black Swan? You've probably heard of it, right? Heard the concept of the Black Swan that comes from the book, The Black Swan. Okay. The idea is the idea of how humans discount improbabilities. The main point that he makes is still, this goes back to your question.
Yeah.
He makes the claim that none of our financial theories have any value. Okay.
There's no knowledge.
And his basis for explaining why that's true is because we are using Gaussian theories on the market. We're saying, what are the odds of, what's your risk based on the variance that exists on this stock? And then the risk is supposed to be based on a Gaussian delta. It's what the chances you're going to have a Six Sigma event that should only happen once in the history of the universe. Well, which companies you mentioned is Goldman Sachs. On their stuff, they had like a Six Sigma event every single day. Okay, so which just means the model's wrong. But what he's pointing out, it's not just a matter of the model's wrong, the whole math is wrong. You should not be applying Gaussians to the market at all. Anything you do with the market with the Gaussian is, by definition, wrong. Okay. Now, as it turns out, though, when I read the book, I was actually kind of scared. It's like, man, however, as I further more, read more, there are so many things where we use Gaussian that are like that, and they actually do work, even though they're not really Gaussian.
Yeah.
And so, like, it's so common, and it works often enough that, I don't know, I mean, his argument, you can apply it to a lot of things you probably wouldn't want to apply it to, right? So, but there's still an open question. Is it right to be using it for software?
Well, when the rest of the economy is tied to it, probably not, but who knows? I don't know. I mean, to me, I haven't read the Black Swan, but to me, the main point is that, like, Thomas Friedman's famous for the world is flat, right? So thankfully, somebody came up with an intelligent response to that book. Sorry, I didn't like that book, but it's called The World is Curved. And it kind of makes the same point. Like, we don't know what's over the horizon, actually. Like, for all this mass information in the world today, things, because I took investing way back when I was in Silicon Valley at Foothill College. They had some investment guy gave some little class on, my dad had just passed away. I was taking care of stocks for the first time. And he taught me something that was really important. He said, whatever the current financial circumstances are, that's what people think it's going to be in the future. If you go back to 1981, the mortgage rate, the best mortgage you would get was 19%. If you had bad credit, you're paying 24% on a mortgage. And then that's what everybody thought it was going to be like. And then today, what everybody thinks, what we've had for the last, up to 17 years, depending on how you count it, is what people are expecting. But to me, that's the whole point. Like, I think you're right. Like, 99% of the time, you make money and you're productive using these models, and as long as you don't bet the farm on them, then. But I mean, generally speaking, I think people make that mistake. They think that what's going to happen tomorrow is, what has already happened. What's that? Oh, is that what they call it? Okay, yeah. Oh, okay. I've studied a lot of stats, but yeah, I never put that, like, that together. That's a good point. So, okay, stock market predictions. Everybody, no, just kidding. Why don't we give him a round of applause here, and then.
If you ever want to scare yourself in the stock market,
Already happened.
the idea that the stock market in general goes up.
Yeah.
Go take a look at the Japanese. Well, it's true.
No, you're right.
Still, go look at Japanese. That it is not true